the fourth part of lecture 6, um, and we completed talking about the different aspects of stereolithography, the resin systems, the reactions, and things like that. And now we are going to talk about um, extrusion based uh, rapid prototyping or additive manufacturing processes. I could have described the different um, extrusion based processes based on the Stratasys machine, but I thought rather than just describing what you could probably find in the in the literature or by Googling that or by looking at some YouTube videos, I thought I will talk something about some of the earlier things that we did that I was a part of, um, especially regarding adapting the extrusion based processes for ceramics, because that is one of the techniques that was developed in the mid 90s. So that's how long additive manufacturing has been around. So in those days, we used to call the 3D printing or additive manufacturing for ceramics as solid freeform fabrication. I mean, this was for everything, but mainly for ceramics, we used to call that solid freeform fabrication. So there were many techniques that people had adopted at different places. Um, so the first one was the regular 3D printing. If you recall, this is based on a powder-based process. So you just inject some kind of a binder system that binds the powder particles together. This was originally developed at MIT and then was taken over by a company, an Israeli company called Soligen, mainly for shell molding processes for the foundries. And I'm not really sure if Soligen is still existing or not. Um, there was a technique that was called computer aided manufacturing, and this was uh, again, if you go there, I mean, if you Google this process, you might be able to find some additional information. This was developed at Case Western. Laminated object manufacturing, which was developed by a company called Lone Peak in Utah. Then we had the fused deposition of ceramics that was developed by Rutgers University and Allied Signal, along with a company called Advanced Ceramics Research, where I used to work. Then there was a technique called extrusion free-form fabrication, which was more um, again an adaptation of the fused deposition process. And then there was a process called shape deposition manufacturing that was originally developed by Stanford and Carnegie Mellon. And then it was we at ACR had adapted that process. And to be to note is that fused deposition of ceramics and extrusion freeform fabrication are both based on the fused deposition modeling process originally developed by Stratasys. So here I'm going to talk more in terms of these two processes, and these are both green ceramic uh, additive manufacturing processes for ceramics. And again, these are built from ground up using the Stratasys technology, which is, if you recall, you put it through a heated nozzle, and again, you are adding thermoplastic binder systems to the ceramic powders. So you have squishy material that is coming out of uh, the heated nozzle, and then you can just bond the particles together because of the heat. So again, I'm going to talk more in terms of extrusion freeform fabrication. I will probably post um, uh, a paper about the fuse deposition of ceramics. Um, One of the earlier papers. I will post that for all of you to take a look at. And in this case, the extrusion freeform fabrication is we have extrusion head into which we place a feedstock that is about 6 inch long and about approximately 3/4 of an inch in diameter. And we had come up with a high pressure extrusion head, and we attached that, adapted that to the Stratasys 3D modeler that you may have seen, which is something similar to the MakerBots. So you are extruding the material from a feedstock bar rather than a feedstock filament. So we had one of the earliest projects that we had was to develop a silicon nitride feedstock material, and we had to demonstrate that we could make complex ceramic parts. In this case, we wanted to make a 46 bladed disc, or we called it blisk, and this was mainly for uh, high temperature engines, so that you could it could go to the engine could go to much higher temperatures than what was possible with the other types of uh, parts. So in this case, we had a high pressure head, and we placed the feedstock material here. No, I'm sorry, feedstock material here, and this piston rod would press it down and apply a certain amount of pressure that we set on the computer, and it would be able to heat up this material up to 420 degrees centigrade maximum. And this was because we wanted to deposit different kinds of materials, including polyaryl ether ketone, which is a thermoplastic material, filled with uh, short carbon fibers. So we used that for ceramics also. So this was the feedstock material, and we had the inside was a ceramic, the outside was um, a boron nitride cell, very very small cell. So this one is about 0.625 inches, and the outer edge, which is the green edge, is approximately 1/32 of an inch thick. And this would help this feedstock material easily flow through that heated nozzle. So comparing the fuse deposition of ceramics versus extrusion free-form fabrication, the fuse deposition is done with continuous filament, uninterrupted build cycle, limited materials, but in this case, we had to keep feeding it with a different feedstock material. We could, so because of that, we had to interrupt the build cycle. Unlimited materials, we could press it down with high pressure and produce parts that needed low or high viscosity materials. But in this case, we were only able to apply low pressure and low viscosity materials because it is a feedstock, it's a filament material. You can only apply a very small pressure going through that nozzle material. So in this case, we had to create feedstock that could be easily extruded through that nozzle. So let me go to showing the different kinds of parts. So this was the bladed disc, and after sintering, of course, because this is sintered in a powder bed of uh, carbon, so sometimes that carbon can interact with the silicon nitride material and leave behind some kind of color difference, but it doesn't do any harm to the mechanical properties of this bladed disc itself. So The main thing is that we need to have good low viscosity materials for extruding through that high pressure nozzle. So it needs to have a Newtonian response. So the higher the pressure you apply, lower should be the viscosity. So that's what this shows. It shows that as you increase the shear rate, the viscosity should actually go down. And there is a critical solids limit because you can't go beyond approximately 25-30% um, solids limit. I mean, you can, ideally it should be about 15%, but we can go to 25-30%. So this is again, it's a dynamic shear response, viscosity versus frequency. So the faster you extrude it, the lower will be the viscosity. So this is what it again shows, and it shows a Newtonian response or shear thinning response. So that's what you require in order for it to be fitted through the extrusion nozzle. So, and higher the temperature, lower will be the viscosity. So if you increase the temperature, you can extrude it much faster. So what we had to do was, we had to show that you could make very nice and uniform part dimensions when you apply the material through that nozzle. If you don't optimize the processing conditions, what happens is that this perimeter is being started from this point onwards and it comes and stops here. So when it stops here, it doesn't stop immediately. So it has to stop here so that the material will still keep extruding, and if you are not careful, it will extrude extra material here. So what we had to do was, we had to make sure that the extrusion nozzle stopped here so that it is still extruding, but it will complete here. And then it will go and deposit more material on top of the previous layer that has already been laid down. So we had to go through a design of experiments process in order to optimize the processing conditions. So these are some of the conditions, and these are some of the parts that we built. This is uh, just a funny shape. So if you look on Google, you can find all these things. But this one is a engine blade for a turbine turbo pump. Okay, so you can see that you can clearly make some very nice and uniform parts. So we built some really large parts until about um, maybe like 5-10 years ago. This was the largest part that we had built, that we had ever built using any kind of process, any kind of additive manufacturing process. And this one was a 7.5-inch bladed disc. And we pressureless sintered these parts to 97% density. So these are very good mechanical properties, and you can also make them directly from the CAD model itself. So we made, but when you sinter them, they would reduce in thickness, reduce in thickness and dimensions, because when you sinter, there is a volume shrinkage that is going to take place. And what we also found is that when you make these parts, if you cut the part, you can see that there are some internal um, process defects, but there is no delamination between the different layers. And after optimizing, we were able to completely eliminate any kind of defect, processing defects inside this part. Of course, I mean, um, this is a part that is brittle ceramic, so you are going to find a ceramic type of a failure when you break these samples. So that's about what I have in this uh, part of the lecture. and I will continue with the next lecture later.